Okay, grab your hard hats. Let's jump right into this quick explainer on the crucial mathematical steps for sizing a safe, reinforced concrete beam.
Before a single drop of concrete is poured, we actually have to subject our beam to a rigorous mathematical stress test. We're constantly balancing our initial estimations against the hard structural truths of forces and material limits. So how exactly do engineers ensure a beam won't just sag or snap under pressure?
Step 1. Deflection control. To prevent any excessive sagging once a building is actually in use, this initial phase is all about the rule of thumb. We're basically setting up a hypothesis for our beam's geometry that we'll rigorously test later on. We do this by estimating the effective depth, using a standard span-to-depth ratio, and then of course adjusting for safety. So the crucial starting point here is that for a simply supported beam, your standard span-to-effective depth ratio, or L/D, is firmly set at 20.
Let's look at a quick example. If your clear span is 6,000 millimeters, well, dividing that by 20 gives you an absolute minimum effective depth of 300 millimeters just to keep that deflection in check.
But as engineers, we absolutely love a margin of safety. We actually often use an L/15 ratio for our initial guess instead, which bumps us up to 400 millimeters. And if we throw in just a little extra buffer, we can assume an effective depth of 407 millimeters. That gives us plenty of breathing room.
Step 2. Calculating maximum internal forces.
Now, before we can finalize that 407 millimeter depth, we really have to calculate the invisible internal forces at play here. Think of bending a plastic ruler. This diagram brilliantly illustrates how a uniformly distributed load physically flexes our simply supported beam, creating this parabolic bending moment that peaks right at the center.
For our calculations, we'll subject our beam to a uniform design load, or WU, of 18.9 kilonewtons per meter over an effective span of 6.25 meters. And this is absolutely crucial. This load includes a 1.5 partial safety factor applied to our dead and live loads. Why? Because at the end of the day, human lives depend on it.
This table breaks down the hard truth of those loads. Running the numbers, our maximum bending moment at the center hits a massive 92.38 kilonewton meters. Meanwhile, the shear force that's quite literally trying to slice the beam at the supports hits 59.1 kilonewtons.
Step 3. Checking required flexural strength.
All right, this is the climax of our structural test. We use this required effective depth formula to see if our assumed 407 millimeters can actually withstand that massive bending moment without failing. We're checking our internal forces against the raw physical limits of our materials.
So by inputting the constants for M20 concrete and Fe415 steel, our formula constant Q becomes roughly 0.138. And here's some fun engineering trivia for you. This specific constant is actually derived by strictly limiting the concrete's maximum compressive strain to 0.0035 before it crushes. Pretty cool, right? Combine that with a 250 millimeter width, and we have the final pieces for our calculation.
Crunching all those numbers, we find that the absolute required effective depth for flexural strength is exactly 365.89 millimeters.
The final safety verdict. Cue the sigh of relief, because our safely assumed depth of 407 millimeters is comfortably greater than the technically required 366 millimeters. The section passes. It's under-reinforced, highly ductile, and, most importantly, structurally safe.
Just as a final practical note here, always remember to add your clear concrete cover and your stirrup diameters to your effective depth. That's going to give you the final overall physical depth, or capital D, of your entire beam.
By manually checking both the deflection limits and the flexural strength, you ensure your beam is completely functional and safe, and you build incredible engineering intuition along the way. But with the massive rise of AI and modern structural tools, is it time to let software handle these complex calculations in a millisecond, or is manual math still king? Well, I'll let that dictate your next design.